Okay. Next is that fast decoupled load flow. Here we cannot solve numericals now, right, but we will tell you what is this one, right. Now, the diagonal elements of J1 described by equation 57, this is equation 57, right. It can be written as delta pi upon delta pi upon delta I sigma k is equal to 1 to n V I V k y I k sin theta I k minus delta I plus delta k minus V I square y I sin theta I. That means, this equation 57, this is your equation 57, right, this is 57. So, this one what you can do is that delta pi upon delta I is equal to sigma k is equal to 1 to n, right. This equation is k not is equal to I, this equation, right, V I, then V k, then y I k, then sin theta I k minus delta I plus delta k. This is the diagonal element, right. So, with that what you do, you just look what I am doing, add your V I square, then y I, right, then sin theta I minus again subtract V I square y I, then sin theta I, right. If you do so, then this term you bring it to this into this summation such that k not is equal to I you remove, because the ith term when k is equal to I, for example, when k is equal to I, it will be V I square y I sin theta I. So, V I square y I sin theta I. So, that is why you bring this term into that means this one it can be written as k is equal to 1 to n V I V k, then y I k, then sin theta I k minus delta I plus delta k, then minus this is separate term V I square y I, then sin theta I, but k not is equal to I now is removed, because this term has brought into this summation, right. If it is so, then this first decoupled thing, first thing is that this term can be written as whatever I showed you, that this term minus V I square y I sin theta I. That means, delta pi upon delta I, right, it can be written as your sigma k is equal to 1 to n V I V k y I k sin theta I k minus delta I plus delta k minus V I square y I sin theta I. This is equation 65, right. Now, using equation 65 and 51, right. So, in equation 51, that equation 51 q I is equal to actually minus of your k is equal to 1 to n V 1 V k y I k sin theta I k minus delta I plus delta k up to this, right. So, that expression, this expression actually you put q I is equal to that expression minus of that one. That means, this expression is equal to minus q I, that is why this expression you go to equation 51, then you will see that q I is equal to minus of this whole expression up to this, right. That means, this expression is equal to minus q I. So, I am not going to 51, it is understandable now. So, this term is written as minus q I minus this term V I square y I sin theta I. This way you can write, right. Or next is that delta pi upon delta I then is equal to minus q I, and y I sin theta I is equal to b I, because we have taken the convention once that y is equal to g plus j b, right. So, that means, y sin theta is equal to your b. So, y sin theta I magnitude is equal to b I, right. This is actually your conductance susceptance, this is susceptance one, right, b I. This is equation 66. So, this is minus q I minus v I square b I, right. This is delta p I upon delta I. That means, here actually fast decoupled load flow means a several approximation, right. then this one, then BII is equal to YII sin theta I, that is imaginary part of the diagonal elements of the bus admittance matrix, that is capital Y, right. So, in a practical power system, in BII greater than much greater than QI, remember this is actually in per unit values. When you transform your QI, I mean Y is in your Y is in your per unit, Q also is in per unit, at that time you will find that BII is much greater than QI, and hence we may neglect QI in equation 66. That means, in this equation you neglect QI, that means drop QI, right, you drop QI, right. If you do so, then delta Pi upon delta I, right, and another assumption we are making, that this Vi square approximately equal to Vi, because voltage are very in the close vicinity of 1 per unit, because slack bus voltage we are taking 1. So, this is another approximation, Vi square we are taking approximately Vi, and this BII much greater than QI. Therefore, this QI this term is much larger than this one. So, hence this term QI is dropped and Vi square taken as a Vi. So, delta Pi upon delta I is equal to minus Vi BII, this is equation 67, right. So, this is your what you call the delta Pi upon delta I, right. Similarly, just hold on. Similarly, under normal operating condition, delta k minus delta k minus is quite small. Therefore, theta I k minus delta I plus delta k approximately taken as theta I k. Therefore, in equation 58, you please put this condition, that theta I k minus delta I plus delta k. I am not going to equation 58 because here right, in equation 58, right. So, in this is your what you call J1 matrix. So, this theta I k minus delta I plus delta k, right, you just put sin theta I k minus delta I plus delta k approximately equal to sin theta I k, right. So, with this assumption delta Pi upon delta k will become minus Vi V k, and if it is YIK sin theta, if this one if you take, I mean this one for your understanding, that is YIK, that is sin theta I k minus delta I plus delta k. So, what we are taking, that delta I, that your what you call delta I minus delta k, they are they are very small, approximately, I mean difference is very small. So, that means this YIK, that this can be taken as sin theta I k, right, because theta I k then minus delta I plus delta k approximately is equal to theta I k. This one YIK sin theta I k is equal to your BIK, right. So, this one your just hold on, where it has gone, here it is. Therefore, this one minus Vi Vk Bik, right. The Vk is approximately, again making an assumption, assuming Vk is approximately 1, right. Therefore, delta Pi delta k is equal to minus Vi Bik, this is equation 68, right. Similarly, the diagonal elements of J4 as given in equation 59, right, may be written as. So, diagonal elements, that your delta Qi upon delta Vi, right. Let me see if I get your this thing, this is equation 59, right. Let me see if I get equation, here it is, right. So, this equation, that 59 actually, look at that, very simple, just try to understand. Delta Qi upon delta Vi is minus 2 Vi Yii sin theta I, then minus k is equal to 1 to n, k not equal to I, Vk Yik sin theta Ik minus delta I plus delta k, right. Now, this is minus 2 Vi Yii sin theta I. So, take one out, this is minus 2 V I y. So, what you do V I y I sin theta I, you put 1 inside this sigma, take in the summation such that k is not is equal to I should not be there, and another minus V I y I sin theta will be outside, right. Take 1 inside and 1 will be outside. That means, this delta q I upon delta V I, it can be written as, from this equation only it can be written as, right, that is written that minus V I y I sin theta I, this is written, and another V I y I sin taken inside the summation, and k is equal to 1 to, it has included in the summation k is equal to 1 to n, but k not is equal to I, that is V I V k y I k sin theta I k minus delta I plus delta k. This is equation 69, right. So, this is little bit mathematics, but simple mathematics, right. So, using 69 and 51, right, then you will get the same thing, this 51 q I is equal to actually minus k is equal to 1 to n V I V k y I k sin theta I k minus delta I plus delta k. That is actually equation 51, q I expression is equal to minus of the whole term. That means, your delta q I upon delta V I will be minus V I, then y I, then sin theta I plus q I, because q I is equal to minus of this thing, right. That means, this that means I am writing using equation 69 and 51, right. So, this is 69 and 51, I told you that equation already have been given, already those things have been given. So, delta q I upon delta V I will become minus V I y I sin theta I plus q I, but y I sin theta I is B I. So, minus V I plus q I, and with the same assumption that B I is much greater than q I. Note that I told you earlier also that it is this values q I and B I both must be in per unit values, then this condition holds B I much greater than q I, right, and q I may be neglected in equation 70. So, drop this one, you drop this one. If you drop this, then delta q I upon delta V I will be minus V I B I. This is equation 71. Similarly, assuming again theta I k minus delta I plus delta k is equal to theta I k. So, equation 60 can be written as, right. So, this is your equation 60, this is your equation 60 with the same assumption, this is equation 60. We will take this one as a sin theta I k such that it will be V minus V I B I k, right. That is why this one delta q I upon delta V k will become minus V I B I k. With this assumption, and equation 60 can be written as, this is equation 72, right. That means, in general, so we have what we have seen is that delta p upon V I magnitude V I is equal to actually minus b dash delta delta, this is equation 73 in matrix form, and delta q upon V I is equal to minus b double dash say delta v, b dash into delta v, this is equation 74. So, that means, this equation everywhere multiplied by V I and B I or B I k, that is why this is one set of equation, this is another set of equation. Now, this b dash and b double dash actually these two matrices, right, they are independent of any your what you call any variables, like I mean it is a constant, right, totally independent. So, you need not evaluate them in every iteration, right. So, it is a constant matrices, and only if you invert them once and that is all, but you need not evaluate again like Jacobian matrix, right. So, this is your the decoupled and fast decoupled powerful solution require, but in this case fast decoupled case that you need, it is very fast computation, but perhaps it takes more iteration, than the decoupled Newton-Raphson method, right. But although it takes more iteration, but computationally this is very efficient for transmission line, right. So, this was proposed by Stott and Alzac, if I recall the year correctly, probably it is 1974, right. So, this one your first decoupled load flow. So, this is the matrix. So, numericals other things I cannot show you because already two examples are given, right, time is permitted. and but for small example or some other type of problem, sometimes fast decoupled it does not converge, right. But for high power transmission line it is very efficient, and commercially packages packages are available, right. So, this is equation 74. The whole thing can be represented by matrix, right. So, this is your fast decoupled load flow. Once this is done, right, next we will come to that your what you call the tap changing transformers, and rather I will say that transformer representation in the load flow studies, that is the pi equivalent, right. We have seen little bit a tap changing transformer before, right, little bit ideas have been given. Now, when the tap ratio is at the nominal value, that is when A is equal to 1, right, at that time the transformer is represented by a series impedance, right, series admittance rather, right, YPQ. Suppose you have a tap ratio 1, so you are not changing the voltage level, right. So, in that case it will be represented by a series admittance, right. So, YPQ. So, come to this one. So, this is your what you call the admittance, the representation is something like this. First you have to understand this diagram. Suppose you have a transformer, right, I will come to that A and other thing. So, suppose you have a transformer, this is say P, say this is we call bus bar P, its voltage is Vp, this is bus bar Q, its voltage is Vq, right. So, transformer has impedance, hence the admittance, right. So, this is actually YPQ. For example, this transformer has admittance YPQ, but this YPQ would put in the line as if it is some kind of series connection YPQ, and this has become ideal transformer, right. And this bus bar taken this side, right, this is a fictitious bus bar, they marked as a T, right, this marks as a T, this is a fictitious bus, right. And actually this is one side of the transformer, right, and this is another side of the transformer, high voltage or low voltage or high voltage does not matter, but a fictitious bus is taken and YPQ is the admittance of the transformer, and as if this is an ideal transformer now, and it is 1:A, that is the your what you call trans ratio, right. So, actually this side is NT, right, and this side is NQ. So, it is 1:NQ upon NT, right, that will come later. So, this is the transformer representation, and this side current is going say IP, and this side it is IQ, right, this side it is IQ. So, that means before going to that means if you take that MMF equation, that means NP into I your if this side is NT turns, then NT into IP will be minus NQ into IQ, that will come later, right. So, this is the direction of the current, and this is P and Q, and this is the equivalent circuit of a transformer, and look how we represent it, a pi representation, right. So, that is why I have written that figure 9, this figure 9 shows a transformer with admittance YPQ in series with an ideal transformer, right, representing the off nominal tap ratio 1:A, right, and T is a fictitious bus bar, right, between that ratio and the admittance of the admittance of the transformer, right. That means in between this one, right, in between this one and this side, right, this your what you call this fictitious bus bar we have assumed. Next is before coming to that, right, this is T, this side is T, this side is Q, right. So, we assume this side turn is NT, this side NQ, right. Therefore, T and Q, NT and Q, that means T and Q we can write 1:NQ NT, that means it is 1:A, that means A is equal to NQ upon NT, right. Therefore, from figure 9 we can write VQ by VT is equal to NQ by NT, that means from this figure you can write, right, VQ by VT is equal to NQ by this, you know, right. For example, generally for machine studies and this that you have studied V1 upon V2 or E1 upon E2 is equal to N1 by N2, same thing, right. So, VQ upon VT is equal to N, it is A, that means VT is equal to VQ upon A, this is equation 75. Now, as I told direction of the current, right. this is taken this way, this is taken this way, right. So, this side is NT turn, this side is NQ turn, that means NT into IP is equal to minus NQ IQ, right, because this side is IP and this side is IQ. So, your NT into IP, right, is equal to minus NQ into IQ, right. So, NT this side is NT. So, NT into IP is equal to minus NQ into IQ, right. That means, IP is equal to minus NQ upon NT into IQ, but NQ upon NT is equal to A, here also A, IP is equal to minus A into IQ. This is equation 76, right. That means, the current IP is given by, if you look at the diagram, the current IP is given by this IP is equal to YPQ into Vp minus your Vt. Here if you want, you can put this fictitious bus bar voltage is Vt, right. That means, that IP is equal to your YPQ into Vp minus Vt. Therefore, we write IP is equal to YPQ into Vp minus Vt, right. Now, using equation 77 and 75, right, that means, this is your 75 actually Vt is equal to Vq upon A, right. That means, this Vt is equal to Vq upon A, this one you substitute here, right. If you do so, you will get IP is equal to YPQ Vp minus YPQ upon A into Vq. This is equation 78, right. Again, from equation 76, that means, from this equation, equation 76, IQ is equal to your minus IQ is equal to minus IP by A from this equation, right. Therefore, IQ is equal to your minus IP by A, this is equation 79. Now, from equation 79 and 78, right, we have that IQ is equal to, it is minus 1 upon A, this is minus 1 upon A, and IP you substitute here, YPQ Vp minus YPQ upon A Vq, you substitute here, right. If you upon substitution, right, you will get IQ is equal to minus YPQ upon A Vp plus YPQ upon A square Vq, this is equation 80. Now, equation 78 and 80, put them in matrix form, that is IQ is equal to YPQ minus YPQ upon A minus YPQ upon A, then YPQ upon A square, this is Vp Vq, this is 81, equation 81, right. Now, we have to obtain from this equation an equivalent pi model for the transformer, right. How we will do this? So, what one can do is, this equation we have got, right. What one can do is, look, this YPP, that is the diagonal that YPP diagonal elements is equal to YPQ, this diagonal element first one. So, YPP is equal to YPQ. Now, what you do, you subtract minus YPQ upon A, then add YPQ upon A. So, in that case you will get YPP is equal to this YPQ upon A plus this one you take A minus 1 upon A YPQ, right. So, adding YPQ upon A, subtracting YPQ upon A from that, from this thing. So, you will get YPP is equal to YPQ upon A plus A minus 1 upon YP, this is equation 82. Similarly, your YQQ is equal to YPQ upon A square, this one, this is YQQ, right. So, this one your YQQ is equal to YPQ upon A square, in that case also you add YPQ upon A, subtract also YPQ upon A. So, in that case what we will get YPQ upon A plus 1 minus A upon A square YPQ, this is equation 83, right. That means, what we are doing actually, that means YPP will be YPQ upon A plus your A minus 1 upon A YPQ, and YQQ will be YPQ upon A plus 1 minus A upon A square YPQ, right. So, if you look like this, then you can represent the transformer that this P side actually, that is, this is non-tap side, and Q side actually tap side. This P side is non-tap side and Q side is the tap side, right. That means, this is the non-tap side, the P, and Q is the tap side. So, this is Y P P when you write, it is Y P Q upon A, this is that your transformer, your admittance Y P Q upon A, and with that this is your shunt branch is coming for the transformer, that is there is a shunt part, that is your A minus A upon A Y P Q. If you write Y P P, this is Y P Q upon A plus A minus A upon Y P Q, right. Similarly, if you go for Y Q Q, that Y Q Q, right, this side it will also Y P Q upon A, Y P Q upon A is there plus 1 minus A upon A square Y P Q, 1 minus A upon A square Y P Q. When tap ratio is at nominal, that means A is equal to 1, there is it is simply Y P Q, right, and when A is equal to 1, this term will not be there, it will be 0, this term will not be there, it will be 0, and transformer can be represented just as series admittance if A is equal to 1. If it is not, this is the pi equivalent of the transformer model, right. I hope this equation you have understood, this is very interesting, right. So, how what way we have done it, right. So, that means suppose you have generator, right, you have a generator, for example, you have a generator, right, then you have your what you call transformer, this is transformer, right, then it is going to transmission line, your step up transformer, say transmission line, you have the transformer, right, and transformer, for example, suppose I am just showing transformer may be in step down, step up, anywhere in the line, right. For example, then again you have the transformer, say you are stepping down the voltage, suppose this is 11 kV generator side, say this is 220 kV, this is also say 220 kV, right, 220 kV. So, this is also, and say this is your say 66 kV side, right. Suppose this suppose for example, this transformer you are representing, right. So, in that case this is your 2 bus bar, right, this is your 2 bus bar. So, this will be your Y P Q by A, right, this side, and this side is your that transformer shunt side is there, this is A minus 1 upon A Y P Q, right, and this side also it is there, this side also it is there, it is 1 minus A by A square Y P Q, right, and in addition to that your what you call that other your what you call line charging admittance and things are also there, right. So, but when if A is equal to 1, then simply it can be taken as Y P Q, but if A not is equal to 1, right, some other values depending on the increase or decrease of the tap whatsoever, right, then this branch, this shunt branch also has to be considered, right. That is the idea of the your what you call that tap changing transformer, right. It is not tap change, that is transformer pi representation, sorry, pi representation, right. So, this is the idea, and this is that pi equivalent representation of the transformer, right. So, with this, right, with this what we will do that just today we will discuss, just we will discuss, and after that we will come to that. Generally, now at present in that power system, that 2 new more buses have been introduced, that is called P bus and P Q V bus, right. That means, suppose this that means at a bus where P is known for P Q V bus, right. Here P is known, that is real power is known, very interesting it is, your Q is known, this is also known, and voltage magnitude is also known. These 3 quantities are known for PQV bus, unknown is only that voltage angle delta, this is actually unknown quantity, right. And P bus, when you take the P bus, that is only P is known, right, but your Q, then V and delta of the P bus, they are actually unknown quantities, right. So, why we will go for your P bus and P, I mean P bus, if you take PQV bus means P bus has to be there, these two bus has to be there, right. So, question is why we will go for PQV bus. Actually, when you want to control a remotely located bus voltage, so you can control it from another bus, but judiciously you have to take in the network which one you will take. For example, I am giving you a for your understanding a simple diagram. Suppose you have a this kind of network, say just showing one generator, right. You have a this kind of network, detailed mathematics other thing will be given later, right. You have a just for the understanding, right. Suppose you have a network like this, you have a network like this, just I have made it like this, right. So, this is say this is bus 1, right, just hold on, this is bus 1, just number it, arbitrary numbering 2, 3, 4, 5, 6, 7, 8, right, 9, 10, 11, 12, then 13, 14, 15, 16. So, this is 16 bus problem. This is your slack bus, say, right. Suppose my bus 8, say my bus 8, if I make it as a PQV bus, right, and I want to I have to and from as P and Q both are known, this is not a PV bus, PQV bus, as Q is known, that means I cannot inject further Q on bus 8. So, I cannot control this voltage, but I want the my bus voltage magnitude is V8, suppose I want to maintain at 1.0 per unit for example say, but I want to control this bus voltage magnitude from a remotely located bus, that means not from this bus, but some other bus, right. For example, I can I will only on this network I will find out that which node, from which node I want to control this your what you call bus voltage magnitude, right. So, what one can do is first I can choose say bus 2 is a P bus, that suppose this is PQV bus, you have to choose one P bus, but which P bus will be a best bus based on the your loss reduction you do not know. First we have how mathematics Jacobian can be formed will be seen later. First suppose I have chosen bus 2 is a P bus, right. That means at this bus I have to inject Q such that I can maintain this voltage at 1.0 unit and I have to check the loss also, right. Similarly, I can choose the bus 3, right. So, in that case I have to find out what will be the Q injection such that I can maintain this voltage and at the same time of the power loss. So, similarly, each bus I have to test and I have to see which one is giving the minimum loss, based on that I will choose the your what you call P bus. For example, suppose bus 3 is giving my best your Q injection for which my power loss of the network is minimum and I can maintain this voltage at 1 per unit. That means, instead of PV bus, PQV bus, that means this bus voltage magnitude you are controlling from a remotely located bus. But if you try to make it from here I will control, you cannot do that because it is a radial network. So, no connectivity or this node actually is not coming here. So, it is almost you will get some you know not desirable desired result. So, it is a radial network I have taken just to make you things understand, right, P bus and PQV bus. If it is a transmission loop system your mesh distributed network, transmission network, you have to see that which bus you choose PQV bus, but which bus should be P bus, accordingly you have to choose, right, based on many factors. That means that P bus and PQV bus load flow studies you have studied, but these two buses you have not studied because it is not available in the book, right. So, later we will discuss that formation of Jacobian matrix, taking a small example that how PQV bus work, but I can tell you regarding this P bus and PQV bus we have made the simulation other things and your what you call using Newton-Raphson method and results are very encouraging, right, and some significance will be there for this P bus. We will discuss later, right, about this one. So, thank you.